8.2 to 8.3 are the graphing sections of this chapter. This is for graphing rational functions. A rational function is f of x equals p of x over q of x, where both p of x and q of x are polynomials. The steps to graphing are to first find the vertical and horizontal asymptotes. Then you'll want to plug in x values to find points on the graph, and you want to find the x-intercepts if you can. And then you're going to find the domain and range. For the horizontal asymptotes, it's going to be at y equals 0 if the degree of the numerator is less than the degree of the denominator. The horizontal asymptote will be at a sub m over b sub m if the degree of the numerator equals the degree of the denominator. So in the examples below, I have y equals 3x squared over 2x squared, so the horizontal asymptote are going to be the ratio of the coefficients, so 3 over 2. And then same with y equals 5x over 7x. Since the degrees are both 1, that means the horizontal asymptote will be at 5 over 7. And the last one is called a slant asymptote. This is when the degree of the numerator is the degree of the denominator plus 1. So if it's 1 more than the degree of the denominator, then we're going to divide, and whatever equation you get is going to be your slant asymptote. So in the examples, we want to graph and find the x-intercepts if there are any: domain, range, vertical asymptote, and horizontal or slant asymptote. For number 1, we have y equals 10 over x. The x-intercept is when we set the numerator equal to 0, and the numerator is just 10, and we can't set that equal to 0, so there's no x-intercepts. Then for the vertical asymptote, we're going to set the denominator equal to 0. And our denominator is just x, so the vertical asymptote is going to be at x equals 0. Domain will always be at x can't equal whatever the vertical asymptote is, so it's going to be at x can't equal 0. Then for the horizontal asymptote, that's using the chart that we just discussed. So the degree of the numerator is 0 because we don't have an x, or we have an x to the 0 power, which is 1. And then in the denominator, we have x to the first power. So the degree of the numerator is 0 and the degree of the denominator is 1. So since the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote is going to be at y equals 0. Okay, so for my graph, I'm going to start by drawing the asymptotes. And then I'm going to plug in some points. So the equation was 10 over x. So I'll plug in 1, 2, 5, and negative 1, 2, and 5. So I'll get 10, 5, 2, and negative 10, negative 5, and negative 2. So you can kind of just pick whatever points you want and graph them. And I chose these because they made the equations equal to whole numbers. So we can use the two asymptotes to kind of help us with the shape of the graph. And this is what the graph will look like. For number 2, we have y equals 10 over x plus 7 minus 5. So this time the x-intercept is a little different because we have that minus 5. So what we're going to do is plug in 0 for y. So we'll get 5 equals 10 over x plus 7. Then to solve, we're going to cross multiply. So that'll be 5x plus 35 equals 10. So we get 5x equals negative 25, and we get x equals negative 5. So negative 5, 0 is our x-intercept. The vertical asymptote is going to be when the denominator is equal to 0. So we get x equals negative 7. So that means the domain is that x can't equal negative 7. Then for the horizontal asymptote, if we looked at just this part, it would equal 0, but we have a minus 5. So the horizontal asymptote is going to be at y equals negative 5. Oh, sorry, I forgot to do the range for this one. If we look at the graph, y could be any value except 0. So the range is going to be at y can't equal 0. Okay, sorry. So for this one, I'm going to start by drawing the asymptotes. So we have a vertical one at negative 7 and a horizontal one at negative 5. Then I'm going to plug in points. So if you look at the graph here, our vertical asymptote actually breaks up our graph into two parts. There's one part here and one over here. So when we're picking x values, we want to make sure that they go into both. So like don't just choose 0, 1, 2, and all the positive numbers because we won't get any of the other side of the graph. So I want to plug in a point that's less than negative 7, so I get a point on the left side of the graph, and I'll choose negative 8 because I'll make the denominator equal to 0, and the y value would be negative 15. And I also want to choose a point to the right of negative 7, so I'm going to choose 3 because I'll make the denominator equal to 10, and 10 over 10 is 1, so this will equal negative 4. So we have 3, negative 4, and negative 8, negative 15, which will be somewhere down here. And we can use the asymptotes, so the pink lines, to help us determine what the graph will look like. And you can plug in more points if you want your graph to look more exact. But this is just a rough sketch. Okay, so now going back to the range, our y values could be anything except y equals negative 5. So the range is y can't equal negative 5. Okay, next problem we have y equals x plus 1 over x squared plus 5. The x-intercept is when the numerator equals 0. So we get x equals negative 1. So our x-intercept is at negative 1, 0. The vertical asymptote is when we set the denominator equal to 0. So then we'll get x squared equals negative 5. And there's no real solutions to this. We'll get an imaginary solution. So there's none, which means the domain would be all real numbers. Then for the horizontal asymptote, we're looking at the degree of the polynomials. In the numerator, the degree is 1, and the denominator has a degree of 2. So this is the first case where the horizontal asymptote is at y equals 0. So we have a horizontal asymptote here, and we have a point negative 1, 0 here. Okay, so I'm going to plug in points. I'm going to choose 0, 1, negative 2. I'll get 1/5, 1/3, and negative 1/9. Okay, so I'm going to plot these points now. And this graph is going to be a special case where our graph can cross the horizontal asymptote. The horizontal asymptote tells us what the ends of the graph look like. So the ends of the graph will get closer and closer to 0. And for our range, it could be any value, so it's going to be all real numbers as well. Okay, next one, we have 2x squared minus 3x minus 20 over x squared plus 1. So the x-intercept is when we set the numerator equal to 0. And to solve this, we're going to use the x method, or we're going to factor. So this would be -8 and 5, and on the top would be 2x. So this will simplify to x over -4. So we have 2x plus 5 times x minus 4 equals 0. We're going to set each one equal to 0 and solve. So we'll get -5 over 2 and 4. So that means our x-intercepts are at -5 over 2, 0, and at 4, 0. Then for the vertical asymptote, that's when we set the denominator equal to 0. So we get x squared equals -1. And this is the same as the previous case where we'll get imaginary solutions, so there's none. And domain is going to be all real numbers. For the horizontal asymptote, we're going to look at the degree of the polynomial. For the numerator, the degree is 2 because the highest power is x squared. And the degree of the denominator is also 2 because the highest power is also x squared. So we're taking the coefficients in front of the x squared. So in the numerator, that'll be 1. In the denominator, that'll be 2. So that means our horizontal asymptote is at y equals 2. So at 2, we have a horizontal line. And then we're going to plug in some points. And we can choose whatever we want because there's no vertical asymptote. So we have our x-intercepts, which we're at 4, 0, and -5 over 2, 0. And then we also have these 3 points. So we have 0, -20, which would be down here somewhere. -1, -21 over 2, which would be somewhere here. And then -1, -15 over 2 would be somewhere here. So we're going to get closer and closer to the pink line on the ends. And, ooh, sorry, that was kind of ugly. And our graph will look something like this. So for the range, if we look at the graph, all of our y values were below the horizontal asymptote, so it's going to be at y is less than 2. Okay, number 5, we have y equals 8 over x squared minus x minus 6. The x-intercept would be when we set the numerator equal to 0, but since it's just a number, that means there's no x-intercepts. For the vertical asymptote, we're going to set the denominators equal to 0. So x squared minus x minus 6 equals 0. And to solve this, we're going to factor. So on the top would be -6, on the bottom is -1. So that's -3 and 2. X goes on top. So we have x minus 3 times x plus 2 equals 0. We're going to set each one equal to 0. And we get x equals 3 and x equals -2. So those are where our 2 x-intercepts are going to be. And that means for the domain, x can't equal 3 or -2. Okay, next for the horizontal asymptote, we're looking at the degree of the numerator and denominator. The degree of the numerator is 0 because there's no x and it's just a number. And then the degree of the denominator is going to be equal to 2 because the highest power is x squared. So since the degree of the numerator is less than the degree of the denominator, that means the horizontal asymptote is at y equals 0. So looking at the vertical asymptotes, it breaks our graph into 3 sections. So there's one here, and one here. So when we pick our points, we want at least one point from each section. And usually you'll graph more in the middle section just so you know what the shape looks like. So on the left section, I'm going to plug in -3 and I'll get 4/3. In the middle section, I'm going to plug in -1, 0, and 1. And I'll get -2, -4/3, and -4/3. And in the last section, I'm going to plug in 4 and I'll get 4/3. So now I'm just plotting the points. And on the two sides, we can use the vertical and horizontal asymptote to figure out the shape. So it'll look something like this. And then in the middle, since we plugged in 3 points, we know that this is going to look like a parabola. So range is the possible values of y, and if we look at the graph, y could be any value except 0. So the range is going to be at y can't equal 0. Number 6, we have x squared minus 5x minus 36 over 3x. So the x-intercept is when we set the numerator equal to 0. So to solve this, we're going to factor. On the top would be -36, on the bottom is -5, so that's -9 and 4. So we have x minus 9 times x plus 4 equals 0. We're going to set each one equal to 0. And we get 9 and -4. So that means 9, 0 and -4, 0 are our x-intercepts. For the vertical asymptote, that's when we set the denominator equal to 0, so we get x equals 0. So domain is x can't equal 0. Then for the horizontal asymptote, the degree of the numerator is 2 and the degree of the denominator is 1. So we actually have a slant asymptote because the degree of the numerator is 1 more than the degree of the denominator. So to do this, we're going to use long division. We have x squared minus 5x minus 36 in the denominator, or in the inside, and then 3x on the outside. So our goal is to get cancel out the x squared. So we have to multiply by 1/3 x because 3 times 1/3 is 1, and x times x is x squared. So then when we subtract, this will cancel out. Then we're going to bring down the -5x. And to get from 3x to -5x, we have to multiply by -5/3. So this will be -5x. And then we're gonna, so then this will cancel out when we subtract. And then the remainder would be -36, but we don't have to do anything with this. So this at the top here is going to be our slant asymptote. It's going to be at y equals 1/3 x minus 5/3. So when I graphed my asymptotes, I have a vertical asymptote here and a slant asymptote at 1/3 x minus 5/3. So I'm going to graph this like a regular line. I'm going to start at the y-intercept, which is -5/3, which would be somewhere here. And then I'm going to go up 1 and over 3. Because that was the slope. And so the graph will look something like this. We also have our two x-intercepts, which are at 9, 0 and -4, 0. So I'm going to plot those. And we can use the asymptotes to help us figure out the shape. So it's going to get closer and closer to the pink lines. And the graph will look something like this. Then for this problem, if we're looking at the possible y values, it goes up forever and down forever, so the range is going to be all real numbers.